Good day, everybody. Let's take a look at some connection between the macro and micro properties of certain organic chemicals, right? So today we're going to be focused on the relationships, in a sense, amongst alkanes, then carbonyl-containing compounds, and alcohols. So let's get to the problems right away. So here we go. Problem one. So in this case, we're going to concentrate on the comparison of certain organic chemicals, such as this one, right? So it is an alcohol right here. So then we'll have a similar chain length alkane, and then we'll have a similar chain length ketone, carbonyl compound, right? So right now it is about like boiling point sequence, right? So we're going just to arrange them according to their boiling points from the lowest boiling point to the highest boiling point, right? So if we think about it, so what will influence the boiling point? That's going to be the interactions between the molecules on the micro level, right? So typically, if we look at the interactions between the molecules, we are going to be concerned with the particular IMFs or intermolecular forces that exist between certain molecules, right? So if we take a look at, for example, this alkane right here, so that's going to be just an alkane without any substituents or functional groups on it, right? And then once we think about what kind of IMFs exist in this case, then we will think about dispersion forces. Dispersion forces are pretty weak, so most likely that's going to be our lowest boiling point. Lowest boiling point will be ascribed to the alkane in this sequence of chemicals, right? So then we move on to the ketone, which is going to be about the same chain length, or also 4 carbons, to be honest, as the alkane, but it will have the dipole moment happening in the molecule, right? So as we recall, so there's going to be a partial positive charge on the carbonyl carbon, partial negative charge on the oxygen in the carbonyl group, right? So because oxygen is more electronegative, it will be trying to kind of like draw the electron density towards itself. And then as a result, we are going to have the dipole moment generated in this molecule. So dipole-dipole interactions will be happening consequently between the like multiple molecules of this particular ketone. So dipole-dipole interactions are a little bit stronger than the dispersion forces, and then consequently it's going to be kind of like harder to like boil off these particular ketone molecules, turn them into vapors from the liquid phase to the vapors, right? It's going to be taking a little bit more temperature, higher temperature, right? So consequently, it's going to be somewhere in the middle. So we can say it's going to be medium boiling point. So it's going to be a little bit higher than the boiling point of the alkane, but a little bit lower than the boiling point of the alcohol. We'll see later why. So it's going to be like second highest boiling point, right? So lowest, then a little bit higher, medium boiling point will be ascribed to our ketone in this case. So finally, we're going to take a look at the alcohol. So alcohol will feature the OH bonds, right? So these are lone pairs here, by the way. So then it will have the OH bonds. OH bonds will be able to produce the hydrogen bonding, right? So hydrogen bonding is stronger as an intermolecular force compared with the, for example, like dipole-dipole interactions, right? So consequently, so out of those 3 molecules, it will be hardest separation between the molecules, right, to achieve in the molecules of alcohols, right? So then it will take, consequently, if it's harder to separate the molecules of alcohols, right, than the molecules of the ketone, then the alcohol will have a higher temperature for it to be boiled off and turn into the vapors. So consequently, the alcohol will have the highest boiling point amongst those 3 compounds, right? Lowest, medium, highest boiling point, because alcohol will feature the strongest IMFs, intermolecular forces, that will be present between its molecules. So consequently, the highest boiling point will be ascribed to the alcohol because it's going to be most difficult to separate the molecules of the alcohol due to the relatively strong hydrogen bonding interactions, right, that will exist between the molecules of this particular alcohol, which is going to be 1-propanol, by the way, right? So anyway, so now let's move on to the next problem, which will be a little bit different, but we'll be also looking at the connection between the micro properties, right? The properties on the micro level and the macro properties that will be influenced by the micro level interactions between the molecules. All right, so what are we going to look at? That's going to be the following set of molecules. Right, so we are going to take a look at this one, which is going to be an ether, by the way, right? So just try to look for functional groups and see what you can recognize. At this point, we should be able to recognize a lot of functional groups, which we have seen so far. Then we are going to take a look at this alcohol right here. Last but not least, alkane. So these are the ones, right? And then we're going to arrange them by solubility. So solubility in water, right? So solubility in water from lowest solubility to the highest solubility, right? So let's take a look at, for example, alkane. Alkane, out of those 3 molecules, resembles the molecule of water least. So consequently, we can guess that it will have the lowest solubility, right? So we can also take a look at the molecule itself. Think about the forces that will exist between the molecule of this alkane and the water molecule, right? So looks like we will not be able to achieve any dipole-dipole interactions, which are relatively strong, as well as the hydrogen bonding will be also non-existent. So maybe we'll have some sort of like dispersion forces, right, at best. So consequently, we will not have that much interaction going on between the molecule of the alkane of this kind, right, and the water molecule. So the water molecule will also be not that will also not look like this alkane at all, right? So structure-wise, so consequently, we can use those arguments like dissolves like. So this molecule of alkane and water are pretty non-similar. So it's unlikely that this alkane will dissolve in water just by the like structural argument, right? Also from the interaction perspectives. So the forces that will exist between the molecule of the alkane and the water will be pretty weak, right? So this will not result in a strong interaction, and this will not lead to the like particularly high solubility of the alkane in the water. So probably it's going to be the lowest solubility, right? Let's put it L. Let's give it an L here, lowest solubility. So then if you look at the molecule of the ether, so this molecule is more like the molecule of water. So potentially some sort of like weak dipole-dipole interactions will be able to be generated in this case, right? So because if you look at this, so by the way, so this molecule of ether almost looks like a molecule of water, except instead of hydrogens attached to the oxygen, we'll have a couple of ethyl groups, right? But nevertheless, we're going to have the central oxygen molecule or atom rather, that will also be present in the molecule of water, right? So then in this case, we can say that this molecule of ether looks like, to some extent, the molecule of water, which will contribute to the likelihood of the better solubility of ether in the water than the solubility of alkane in the water, right? So consequently, we can say, well, this solubility will be somewhere on the medium level. So as long as we are comparing those 3 molecules, right? So in terms of their solubility in the water. So then what else? So we can also think about some sort of a little bit like stronger interactions that will exist between the molecule of ether and water, right? So ether will feature the polar bonds between the carbon and oxygen. So we potentially can think about some sort of dipole that will exist in the molecule of ether. The dipole also exists in the molecule of water. Consequently, we are speculating that we will have the dipole-dipole interactions between the molecule of ether and the molecule of water. So dipole-dipole interactions will be stronger than dispersion interactions that will exist potentially between the molecule of alkene and water. So consequently, we'll have a little bit higher solubility because we'll have the higher interaction between the molecule of ether and the molecule of water, right? That will lead to a higher cohesion between those molecules and higher solubility, because the solubility is about the ability of the molecules to stay together, right? To make a solution, right? So just like some things to connect. All right, so consequently, that's going to be somewhere on the medium level. So then if we have a look at the molecule of alcohol, this will resemble the molecule of water even more, right? So again, we'll have the central molecule, central atom of the oxygen, which will also have the H attached to that, just like in the molecule of water. And then we'll have like one point of difference, which will be the fact that in the alcoholic molecule, we will not have the hydrogen over here, we'll have this like alkyl chain, right? So, but nevertheless, this molecule looks even more like the molecule of water than the molecule of ether looks like the molecule of water, right? So, what we can say that by the structural argument, like dissolves like, this alcohol will have the highest solubility in water, right? Also, when we think about the intermolecular forces that will exist between the alcohol and the water, so we can think about the hydrogen bonding. Hydrogen bonding will be stronger than dispersion forces. It will be stronger than the dipole-dipole interactions. Consequently, looks like we'll have the highest solubility for this molecule if we try to dissolve this alcoholic molecule in the water as a solvent, right? So stronger interactions will have the probability to form like very nice solution, right, between the molecule of the alcohol and the water in this case. So lowest solubility, medium solubility, highest solubility, hydrogen bonding plus higher resemblance, right, of the water molecule when we look at the alcoholic molecule. So only like one feature will be different, right? So it almost looks like H2O, HO, but instead of hydrogen, we'll have this like alkyl chain here, right? But anyway, so like dissolves like, this molecule is very similar to the molecule of water, and also this molecule will have the hydrogen bonding interactions that will be present between alcohol, right, and the water molecule. So moving on, let's continue to problem number 3. We're going to erase everything. All right, so what does this problem entail? So at this point, we're going to move on to the reactions, right? So we're going to jump to the chemical properties of the so-called thiols, right? What is a thiol? So thiol is when we have some sort of typically alkyl chain, right? In our considerations, of course, the R group can be lots of different groups, right? It could be something complicated, such as maybe like alkene part, right? So, or maybe it's going to be like an aromatic chain or aromatic part with some sort of alkyl chain and so on. Ultimately, it will be attached to the SH kind of like feature, right? And then here we have the thiol. So that's going to be our thiol. So maybe we'll have the methyl here, ethyl, propyl, isopropyl, whatever it might be. But ultimately, this piece will have to have the SH part as well in order to have the thiol molecule in front of us. So let's take a look at the chemical properties, right? So we're going to get ahead and then look at some example reactions of thiols with the various other substrates, right? That will lead to the formation of unique products, if you will. So let's begin. So this is our thiol example. So two molecules of thiol, right? Let's imagine they're going to react with the heavy metal ions, such as mercury 2+. So what's going to happen? As you remember, so this SH bond will be broken. We will be able to produce H plus as one of the byproducts. And then also we're going to produce S minus, right? So if you look at this two S minus pieces, because we have two molecules of this style, we'll be able to interact with one ion of Hg with the 2+ charge, right? So 2+, minus, and minus. As a result, we are going to have overall a neutrally charged molecule, right? So what's going to be this molecule like? So this molecule is going to be like this. So Hg will form a bond, or rather two bonds, with sulfur atoms present in the former thiol molecule. So the leftover alkyl part will will prevail, right? And it will be looking like this. All right, so this is our molecule. This is our target product, right? So we're going to have the bond between the Hg, which will be able to kind of like produce two bonds, and each sulfur atom will be able to produce one bond. So this is their bonding. So sulfur will provide one bond and one bond. Hg will be able to provide one bond to connect to one sulfur atom and another bond to connect to another sulfur atom. So as a result, this is going to be our product, right? So also we're going to produce two hydrogen ions. If you want to try to like balance this reaction, so here you go, right? So you'll have two alkyl S pieces, alkyl S, two pieces, right? You'll have Hg or mercury, and you'll have two H plus ions or two protons generated as well as a side product. Here they are. Next process. Let's imagine we have something like this. So this is going to be our cyclic thiol. It will be oxidized now. Once this happens, what are we going to do, right? So we are going to predict our product. So as we recall, the SH bond will be broken. So here we have a hint, two molecules will have to come together, literally come together to make the product, right? So, and the product will look like this. So the H's will be kind of like a side product, right? So they will be chipped away from the initial thiol molecule, and they will form some sort of like byproduct, right? Which we are not particularly curious about. What we're curious about is this part. Cycle, alkyl cycle, and S, right? So they will be connected together via the SS bond. So let's show it. Cycle, sulfur. So then another cycle. That's our second molecule, essentially, right, of this thiol. And now, if they both lost H, then they will have those technically electrons available for the future covalent bond formation. And here we go. The bond is formed. SS, or sulfur bridge, that's like what they might call it in biology, for example. So nevertheless, here we're going to form the SS covalent bond, right? So covalent nonpolar bond will be produced. And this is going to be the bond that will help us build our final product, which will look like this, right? So that's going to be our so-called disulfide, right? So that's going to be the result of the oxidation of two molecules of thiol, which will be able to form almost like a dimer, right? So to some extent. So basically we start with a monomer or two monomers, two molecules of that compound, which will be like connected via the sulfur bridge in order to make like a bigger molecule, which essentially is a dimer that is that consists of the two molecules of this monomer, if you consider this thiol and monomer. So this is going to be our molecule, right? Plus some kind of like hydrogen-containing product or byproduct will be produced. We're not going to be concerned at this point by this like hydrogen-containing product, but it's going to be like a side molecule. So just be aware. So this is going to be our main kind of like product of interest. All right, so now let's have a look at the reverse reaction, right? So to oxidation, that's going to be a reduction process. I'm going to erase everything, and we're moving on to this reaction, which looks like that. So we have a sulfur bridge or the disulfide. And now for the interesting part, we're going to have the aromatic ring right here. So this compound, let's imagine it undergoes reduction, right, which is marked like so. So above the reaction arrow, you will have the H in brackets, which stands for reduction. So just for review purposes, from the organic chemistry perspective, oxidation, that's when we mark it as with the letter O in brackets, by the way, right? Oxidation, that's when we increase overall the number of oxygens in the molecule, right? That results, or when we decrease the number of hydrogens. So the reduction is going to be opposite, right? That's when we, for example, decrease the number of oxygen atoms in the molecule and or increase the number of hydrogen atoms in the molecule, which will be formed, right? So here we're going to not change the number of oxygens, right? So it's going to be 0, 0. So as we will see later, but we are going to increase the number of hydrogen atoms indeed, right? So this means that we indeed will undergo the reduction process as far as this molecule is concerned, right? So what's going to be the result, right? So the result will be like this. So let's take a look at the bond breaking. So that starts with some like breaking of the bonds and the making of the new ones once we produce our target compound, right? So the SS bond or sulfur bridge, in other words, will be broken, right? And then in this case, this is going to be a non-symmetric disulfide. So two different sulfides or two different thiols will be produced, right? So just kind of redraw the broken pieces. That's one. And that's the other one. So don't forget the other like things that stay intact. So just be careful whilst redrawing them. So here we go, right? So now we are going to have those kind of like free electrons, right? That will be liberated upon the breaking of the bond. Of course, just a disclaimer, the actual process might be a little bit different, right? So because the mechanism, that's something that we don't consider in our kind of like discourse here. So, but it could be a little bit different, that just kind of, oh yeah, we're going to separate this bond. We will have some free electrons and they will connect with other free electrons on hydrogens, for example, right? So that's going to be just like said for now, right? So for our current intents and purposes, because we are just solely concentrated on breaking of the bonds, right? As in separating two electrons that used to constitute a single covalent bond, right? And then we are going to be concerned at putting together the electrons on these atoms and maybe some other atoms to make new covalent bonds. So that's it, right? So one electron and one electron are separated. Then one electron and one electron are coming together to make the bond, right? So that's what happens here. So these separated electrons will be coming together with the electrons brought about by the reducing agent, right? So that looks like an H. So then why shouldn't it bring the hydrogen atoms, right? So in a sense, that's kind of like what will happen at the very end, right? As we form the like final bonds, right? And the final bonds here will be SH, like this. So you see, it's going to be the covalent bond. One electron from sulfur, one from hydrogen. One electron from sulfur of the other kind of like piece of the former disulfide, and the one electron from the hydrogen brought into reaction by presumably the reducing agent, right? So because reduction is about, in some way, the increase in the number of hydrogens that will be contained by the final molecules. So here we have one unique sulfide, or sorry, thiol, right? SH with the propyl, and we have another unique thiol. That's a single bond, believe me. We have SH piece and like CH2 and the phenyl C6H5 right here. So this is going to be our two unique products which will be formed. Okay, so now we are moving on to the next problem. So let's see what we have here. So I think that is going to be problem number 4. Problem 4. Okay, well done. So we're going now to take a look at some chemical reactions, right? So in our discourse so far, we were looking at the fundamentally the reduction of carbonyl containing compounds, right? So we have seen the reduction that aldehydes and ketones can undergo, right? So this process is pretty straightforward. Just to kind of like recap, let's say we have some kind of like random, like R for random, if you will, aldehyde, such as this one, right? And we might have some sort of like a random ketone, right? R, C, O, R. Okay, so they both can undergo the reduction process that is marked with an H in brackets, like so. Okay, what's the result, right? So as we recall, so this bond between carbon and oxygen will be of interest, right? So both oxygen and carbon will have a single electron, right? That will be able, that like used to uh, be able to come together to make this like carbon-oxygen bond, right? So, but now this bond is going to be broken in order to make new bonds, right? So what are those new bonds, right? So they will be basically the bonds to H's, right? So between the respective carbons and oxygens, right? So as a result, we're going to get something like this. So as you may guess, the geometry will change, right? So we'll not have the trigonal planar anymore geometry here, but rather we are going to have the sp3 hybridization followed by the tetrahedral geometry, right? So of this carbon atom right here. So the bonds between O and H will be formed and CH will be formed. Right, so basically OH bond will be made and CH bond will be made as we undergo the reduction process. So like more hydrogen atoms will be introduced into the given molecule, right? So that's what in like one pathway the reduction in organic chemistry is about, right? So that's going to be about the increase in the number of hydrogen atoms in a particular molecule that results right after the reduction process, right? So here, if you count RCOH, RCOH, and 2 more H's. So that's it. The reduction was manifested. All right. So we have our tetrahedral geometry, by the way, right? So if you were to be kind of like circumspect and diving into details, that's what you may think about, right? So like one of those strategies, right? So just like in general that can be applied to some sort of situation, right, or subject which you are trying to research in detail is just try to generate as many questions as possible that would pertain to this subject, right? So when you want to master something, right, some sort of like technique, sport, whatever it might be, right? So this similar strategy might as well be applied, right? So how do I become, let's say, a better like runner, right? So what kind of diet do I need to have? How many hours do you need to sleep, and so on, right? So this reasoning can be applied to our like this very chemical problem, right? So what about the hybridization of this atom, right, of the carbon versus this one? So we have here how many bonds, right? And what kinds of bonds do we have? What kinds of bonds do we have here? What about the Lewis structure, right? So that will be like kind of like applied to this molecule versus that molecule. So things like that, right? So what bond is broken? What bonds are made? So these bonds are made, for example, the ones that I'm trying to kind of show in sort of bold, right, writing. So this bond is going to be broken, right? So with this squiggle line. So stuff like that. So what kind of thing are we making, right? So we're making the alcohol. What kind of alcohol is going to be, like primary, secondary, or tertiary? It's going to be the primary alcohol, right? So primary alcohols will be made from aldehydes, right? That's kind of the one of the overarching conclusions that we can like apply to this reaction. As you see, just one reaction, right? But we already can kind of like see the entire host of details that surround this like relatively like straightforward, as we will later see, chemical process, right? So anyway, so now we're moving on to another, hopefully straightforward chemical process, right? Which will be the reduction of a ketone of some sort. This CO bond will be broken. So what are we going to have as a result? So let's see what we're going to obtain. Those things will stay, right? Imagine that R and R here are equal, right? So they are both, let's say, propyl groups. Propyl, propyl, right? And then, by the way, as I say that, so maybe it's going to be a good idea to review, right? So if you're not sure what a propyl is, just like draw it, right, on a piece of paper. So this will like help with the like memorization, right, of what certain things are. So anyway, so we'll have now one bond left over between the carbon and oxygen. And now we'll have again those liberated electrons, right, that will be able to interact with hydrogen atoms brought about by your reducing agent. So similar stuff will happen, right? So rehybridization will take place. Then we'll have the like OH group, hydroxy group, by the way, formed. And then we're going to have the alcohol, right? So imagine that if these are propyl and propyl groups, right? Then we are going to have the carbon here with an OH that is connected directly to two other carbons. So that's going to be a secondary alcohol. A secondary alcohol is formed upon the reduction of a certain ketone, right? Just kind of like general rule. All right. What else? Yeah, these are our reduction process. Now let's take a look at something different, right? So we're going to take a look at sort of the prediction of the reactant. So that's going to be our ultimate problem here, which is problem 5. All right, so what is that about? So that is about this. So we have something that we start with, right? So and this something brings us to an aldehyde of some sort. That looks like, sorry, I'm just like looking at my notes. Hence the head motion. All right, so that's the one, right? So that's going to be CO with an H. So this is going to be our like aldehyde functional group attached to some sort of alkyl chain, whatever it might be, like 1, 2, 3, 3 carbons. Like, okay, well, just one example, right, of an aldehyde. All right, so how do we make an aldehyde? So the aldehydes are made upon oxidation of respective alcohols, right? So let's see what the alcohol should be. So it looks like this part, C will stay intact. 3 carbons. All right. So now this kind of like carbon is here, oxygen and H, right? So they also are present in the initial product, which is the alcohol. So, okay, great. So we're trying to build the alcohol from the ketone. So essentially, if you want to go back to this like reactant, you might as well think about the reduction of the aldehyde, right? So that's what we're just now talking about, right? So how once the aldehydes are reduced, alcohols are formed, right? So, and then here we go. So that's going to be our kind of like precursor, in other words, to the aldehyde that we are going to obtain. So we need to like make the respective alcohol out of this aldehyde. Okay, that's it. That's the one, right? So if you think about it, so if this compound undergoes oxidation, so now we're going just to check ourselves, if that makes sense, we are going to do what? So we're going to obtain the aldehydes. So this will be done by breaking this bond and that bond, right? So, and then as a result, as you can see, we're going to obtain 1, 2, CH3 or methylene methyl, methyl, and methylene, CH3, CH2, CH2 will stay, right? So this carbon will stay. This is the carbon right here. So then oxygen will stay, oxygen will stay. So hydrogen will stay, one of them, on the carbon. That's the one, it stays, right? So then we are just going to remove H and H. So then we're going to obtain the aldehyde. So that's it. So basically we need to like reconstruct the alcohol, which was initially used here on the left side to obtain our aldehyde. And that's it, right? So if you want to like think about this from another pathway, it's just going to be, okay, well, we're going to reduce the alcohol, reduce the aldehyde to obtain the initial alcohol, right? And then once this initial alcohol is oxidized, we are going to obtain our like final target aldehyde. So pretty much we kind of like went the entire circle, and then we thought about this from like different perspectives, right? So of course, that's just an example. And a good way for you to practice that is just practice that on paper by looking at like various reactions of this nature. All right, so now let's see how do we obtain a ketone, right? So a ketone can be obtained. We just looked previously at this question, right? So the reduction of the ketone leads to the formation of the secondary alcohol. So in reverse, the oxidation of the secondary alcohol leads to the formation of the ketone, right? So once we have this like underlying thought in mind, we'll be able to crack this problem relatively easily, I hope. So let's imagine that this is our target ketone, which was obtained. So what is it obtained from? From the respective secondary alcohol. Right? So how do we build the secondary alcohol from this? Okay, well, let's redraw the molecule. We are going to add H to O, and we're going to add H to carbon. That's it. That's our secondary alcohol, which upon oxidation will indeed give us the respective ketone, right? So basically you will be able to chop off H and H, and then you'll be able, if you think about this, make this another bond between carbon and oxygen, which will lead to the formation of the carbonyl group and the ketone overall, if you look at the entire molecule. So that's it. So secondary alcohol is our initial chemical or our reactant that undergoes oxidation and gives us this particular product, right? So, yeah, that is it. So maybe, yeah, that's it. So yeah, here we basically keep two like reaction types in mind, right? That's oxidation and reduction. What can we reduce? We can reduce aldehydes and ketones. What will they give us? Primary alcohols and secondary alcohols, respectively. If we want to obtain, like if we want to synthesize, right? So because not only when we consider some kind of class of compounds, right? So not only we're going to be concerned with their chemical reactions, so how they react and then what they make, but also we're going to be concerned with the question, how to synthesize aldehydes or ketones, right? So here we go. That's why we considered this problem, number 5, right? That gives us kind of like our aldehydes and ketones. But now the question is, how do we make them, right? So like, what do we make them from? So basically, the answer is that they are obtained upon the oxidation of the respective alcohols, right? Primary alcohols lead to aldehydes on oxidation of those alcohols. Secondary alcohols upon oxidation give us the ketones. So which is a kind of review if you think about it. So because we did take a look in the past at the chemical properties of alcohols, and then they entailed the formation of the carbonyl compounds, by the way. So yeah, that was in the past, if you think about this from the kind of like overall chemical reactions knowledge perspective. All right, so at this point we are done. So thank you for your attention and have a good time. Bye, everyone.